This is Chapter 3, and a few things about Chapter 3. You need to know Table 3.4. You don't have to know the older names. You do need to know your ions, your polyatomic ions, and that's in Table 3.4. So you definitely need to start working on that, the naming, the chemical symbols, and the charge. The 4 problems that are due for recitation this week are problem 3.2, 3.4, 3.6, and 3.10. We will be talking about ionic compounds, how to name them. You'll need to know this for the exam. Grams, moles, and atom conversions, empirical formulas, percent composition, and balancing chemical equations. Okay, so first let's talk about the ionic compound nomenclature. You need to be able to take a name and write its formula correctly. This is problem 3.1. Now, the first thing you need to do is you need to identify or classify the element. And how you do this is you look at the periodic table. So when I look at the periodic table, I first find manganese. So let's do number 1. Manganese is Mn. And if you notice, that is a transition metal. Now, how else could you tell that that's a transition metal? Well, in this formula, you see the 2, the Roman numeral 2. So this means that manganese is a 2+. So that already gives you the charge for manganese. So chloride is in the halogens, which is group 7A, so it is a -1. If you listen to the lecture videos, you'll find that the halogens have a -1, and then if you go another group, you'll see those are -2. Nitrogen and phosphorus is -3. So your nonmetals have negative charges associated with them. They are anions. And 2/3 of the periodic table are metals. That's right, metals always have a positive charge. And group 1A and group 2A are your alkali and alkaline earth metals, and they always have a +1 charge. The transition metals can have a different charge, a variable charge. So in this case, you need to have the Roman numeral in the name so you know what charge. So in this case, you always want to write the chemical symbol, the charge, and then you need to balance this. In this case, it needs to be, and in most cases, the overall charge needs to be 0. So the quick way I do this, and then you have to check it because sometimes it doesn't work, but this one, I put this is this little subscript 1, which you don't put 1, okay? Because 1's understood. Uh-oh. Okay. Just want to erase that. Well, anyway. And then the 2 ends up being the 2 subscript for chlorine. So that's a 2. So you can put that there, but you don't want to put the 1 as a subscript. So it's Mn, which is understood 1, Cl2. So this is manganese 2 chloride. And so also double check that. So if manganese has a 2+, and there's 2 chlorines, which is -1, that's a -2 overall. A 2+ and a 2- is overall 0. Okay, so let's go to the next compound, which is iron. So we find iron. We look at the periodic table. Iron is Fe. Now, if you look on what to know for the exam information on your modules under Canvas, you'll see that you have a shaded periodic table that you're required to be able to find iron and recognize that it's Fe. So those shaded elements of the periodic table you are responsible for. So familiarize yourself with that. Iron is Fe, and you'll see you need to classify it or identify it so you know how to work with it, but it's a transition metal. So that means it can have a multiple charge. And as you can see here, it has a Roman numeral 3. So that means this is iron 3+. Now sulfide is in group 6A, so it has a 2- charge. So then sulfur 2-. Now what I do is I just going to put the 2 here at the bottom for iron. This is the quick and easy way, and the 3 here for the little subscript for sulfur. And then I'm going to see if that overall charge is 0. So iron, here we have 3+ because of the Roman numeral. And we have 2 of those, so times 2 equals a +6 for the cation. Your cation's always listed first. And then you have 3 sulfurs. This is your anion side, the negative side. 3 sulfurs, and they're each 2-. So what's 3 times -2? -6. So a +6 and a -6 equals sum 0. So we are correct. And so that's number 2. Okay, so looking at number 3. Chromium. So number 3, chromium is Cr. You'll see that it's element number 24 because it has 24 protons. It is a transition metal. And as you can see, it has a variable charge. If you look at the Roman numeral, you'll see that that is its charge. So +2 for chromium. And then oxide is in group 6A, which have a -2 charge, the anion. And then I do the 2 here is going to end up being the subscript for the chromium. And then the 2 here is going to be the subscript for the oxygen. Now, that is not in the lowest terms, okay? So that's not correct. You're not going to see this as Cr2O2. So this is going to have to be rewritten, and it would be Cr oxygen. And then you want to double check. So if you have 1 chromium that's 2+, and in your final formula you never have charges. You would only have subscripts. And the oxide is 2-. A 2+ and a 2- does equal 0, so we are okay. Sum 0. Our next problem is sodium nitride. I'll rewrite down here number 4 is sodium nitride. Let's just double check that. Sodium nitride, yes, sodium nitride. So we look for sodium. Sodium is an alkali metal, so it's in the first group 1. It's going to be a positive +1, Na sodium. Nitride is in group 5A, and therefore it is going to be a 3-. I do my little subscript. I kind of think of it like a do-si-do. And then this will go there. So when you rewrite the subscripts, it's sodium with a 3, and then nitride, and we don't put the 1. So that's sodium nitride, and then we double check it. We don't have any charges in the final formula. Na, there's 3 of them, so that's a +3 for your cation, and your anion is a 3 minus. A 3 plus and a 3 minus equals 0, so that is correct. On to the next problem. Okay, just checking something here. We are looking at nomenclature of ionic compounds, and now we have the element with its charge, and we have the polyatomic anion that you have to memorize. You must memorize these polyatomic ions. They're in table 3.5, page 99 in your Tro book. This is problem 3-2. So this would be a recitation problem that is required for you to handwrite and submit on Canvas. Okay, so in the polyatomic ions, you need to memorize the names, formulas, and charges. So to write the formulas, keep in mind that subscripts are graded, capitalization, spelling counts. You're basically just doing the charges. And I do my shortcut with put the 3 for the subscript for the OH, and then the 1 for the subscript for the aluminum. So I rewrite this aluminum. And since that's going to be 1, I'm not going to write a 1. Now this is a polyatomic. And let me tell you how you recognize it. It has 2 capital letters. Hopefully you have it memorized. But you can always recognize, because there's 2 capital letters, there's oxygen and 1 hydrogen. The oxygen combines with the hydrogen to make a -1 overall charge. Now when you have polyatomic ions, and you're going to have more than 1, in this case we're going to have 3, a subscript 3, you need to have parentheses, only when you have more than 1. So this is aluminum, and then you put your 3 down there. Aluminum hydroxide. Okay? And so that's 3 plus, and then 3 times -1 is 3 minus, so the overall charge is fine. 0. Okay, so let's do number 2. Magnesium is a 2 plus. So that's going to end up being your little subscript for carbonate. You should memorize carbonate is CO3 with a 2 minus. You need to know that. That's carbonate. And we're supposed to actually be writing the names of these. I'm sorry, I see that and now the name. Okay, so let's write this aluminum. And you have to have spelling hydroxide. 2 words. So basically the first cation gets the name of the element from the periodic table, just as it would be from the periodic table. And then you have to memorize in table 3.5 that this is hydroxide. You do not use prefixes. You only use that with molecular compounds. And the reason why is because the charges let you know how many there are. Okay, sorry, let's go back to problem 2. So you're going to have 2 carbonates and you're going to have 2 magnesiums, as you see. Okay, and probably some of you guys are wise enough to realize that that's going to cancel out. But let's just go ahead and write CO3, 2. And then you realize that that's not lowest term, so 2 and a 2. So we can divide a 2 through it. Now, when we do that, we don't need parentheses because we're only going to have 1 of these polyatomics. When you have only 1 polyatomic, you do not put parentheses. So this is magnesium carbonate. We always double check our charges. So here you have a 2 plus cation, and the carbonate you have a -2. That's an overall charge of 0, so you're good. And you want to then write the name of the compound, and like I said, your cation, you just look at the periodic table and you copy that name down, and that's magnesium. the polyatomic anion, you're going to have to memorize that from table 3.5, and you should memorize that and write the exact name down as carbonate, magnesium carbonate. On to problem number 3. So we have lithium. We have 1 lithium, and we have 1. You should have this one memorized. This is a polyatomic anion that you're required to memorize with a -1, and that's called acetate. So 1 and 1, so we're just going to write lithium. Since we only need 1 polyatomic anion, we are not going to need parentheses, so we just copy this down, C2H3O2, and that is lithium, because you just look at the periodic table and you write down the word lithium for your cation, always, unless it's a molecular compound. And then you have the acetate that you have memorized its name from the table 3.5. So it's lithium acetate. And the last problem on here is number 4. And this is a polyatomic cation, NH4 plus. That is ammonium from the periodic table, and once again 1 ammonium plus 1 fluoride, so that would be NH4, no parentheses because you only need 1, and then fluoride, so ammonium fluoride. Now when you are naming, writing the names down, if you look at the periodic table, you'll see that that is fluorine, Fluorine. The element is fluorine. But when it's in a compound, and in this case, and it always will be, an anion, you drop the INE and you add the IDE. So this becomes fluoride. So that's how you get ammonium fluoride. Okay, so we are now on problem 3-3. And we are now converting these formulas, or these ionic compounds in the formulas. Okay, we've already worked a problem like this. As you can see, you have Roman numerals in problems 1, 2, 3, and 4. So that's going to tell you, the Roman numerals tell you what? That is right, it tells you your charge in the compound. So let's do number 1. Copper, you need to recognize it's going to be a transition metal, it's Cu, and I always do like this. I go ahead and put my charges. 1 plus. Bromide is a halogen in group 7A, so that's Br1 minus. And so 1 subscript for copper, 1 subscript for bromide. You don't have to put them, right? Because you don't put the 1s as subscript. And 1 plus and 1 minus will cancel out to 0. So this is copper bromide. Notice you have a capital C and a little u, a capital B and a little br. So do not write them like CUBR, okay? That is totally wrong. The first letter needs to be capitalized and the second letter needs to be small letter. Anytime you have a capital letter, it implies a new element. So let's do number 2. Number 2 is copper oxide. I like to write copper 1 plus because of the charge. Go ahead and write that out. Oxide is oxygen, and it's in the compound name, so it's the IDE, ide, and this is in group 6A, so it's going to be a 2 minus. You need to have that memorized when you see an element in group 6A. Now, the subscript for the copper is going to be the 2, and the subscript for the oxygen will be a 1, so we won't write it. So then when you write this in your subscript, it would be Cu2 oxygen, And once again, you should not write charges in your final answer. Now you want to double check it though. You have two 1 pluses for your cations, so that would be overall 2 plus, and your oxygen, you have 1 and it's a 2 minus. So a 2 plus and a 2 minus, overall charge is 0. Yay, you got that right. And now let's go on to problem number 3. Number 3 is iron. You should recognize it as transition metal Fe. It's the most stable element in the universe. And the charge here in Roman numerals will be a 3 plus. And bromide, see the IDE means it's in a compound. It's bromine, INE, as the element on the periodic table. So bromide here, let's go ahead and read Br. It's in group 7A, so it's going to be a 1 minus. Now we need to figure out what the subscripts are going to be. So iron will have 1, right? So we're not going to actually give it 1. And then, because it'll be understood, and then bromide will be the 3. So this will be rewritten as FeBr3. And then we're going to check it, because we like to check our work. So 3 plus, and there's only one of them because it's subscript. So your cation side is a 3 plus, and your bromide is a 1 minus, and you have a 3 subscript. So that's going to be a 3 minus. Well, a 3 plus and a 3 minus gives you 0. So you can move on to the next problem. Lead. Does anybody know what lead is? You look on the periodic table. It's one of the elements you're responsible for. And lead should be Pb. So what is its atomic number? How many lead? That's where plumbers got their name. Plumber, Pb, because they worked with lead pipes. Yes, it's actually number 82. So that means it has 82 protons. So it's a transition metal, and here it is a Roman numeral of 4. So that means it's going to have a 4 plus charge in this particular compound. And the oxide comes from oxygen. Oxygen is in group 2A. So you have memorized that that's going to be a 2 minus charge. And then we are going to do our subscripts, where lead's going to get the 2, Pb2, and oxygen is going to get the 4. And as you can see, this is not in lower terms, so this will have to change, and this will end up being Pb. Divide 2 by 2 is 1, so you don't write it, and 4 divided by 2, I just divide both of these by 2, will be PbO2. No charges in there, and that's your lead 4 oxide. Next problem is problem 3-4. And I have written on here page 108. So my guess is if you look at Troll, you can look at that problem. Okay, so this is a dimensional analysis type problems. We talked about dimensional analysis in the last chapter. And so we're going to have to look for our given. So our given here, we'll put in blue, is a number with a unit. So you see here that the given in this problem, because you don't see any other numbers with a unit, it's going to be 25.0 milligram. Excuse me. Now, milligram, you know, is a measurement of mass. And that's going to be our given. And we got to have we need conversion factors. CFs, right? We need some conversion factors. And in order to know what kind of conversion factors we need, we got to ask, what is the question asking? So a patient's having an allergic reaction. Takes 25 milligram tablet of the over-the-counter antihistamine diphenylhydramine hydrochloride. You're given the molecular formula. Let me tell you something. When you're given that molecular formula, my guess, before I even start working that problem, is I'm going to have to know the molecular mass of that compound. And as you can see, you have 17 carbons, you have 22 hydrogens, you have 1 chlorine, you have 1 nitrogen, and you have 1 oxygen. And you're going to take that, and we're going to look at that in a minute because I bet you the question is going to ask for that. And you're going to get those molecular masses, the grams per mole, from the periodic table. So, but the question is, how many molecules of diphenylhydramine hydrochloride in this sample? Okay, so you remember when I said if they ask you for how many anything, I don't care how many atoms, how many particles, how many molecules. When you see how many, what do you think of? What conversion factor? Avogadro's number. And Avogadro's number is for 1 mole. You have 6.022 times 10 to the 23rd. In this case, it's going to be molecules. So you will need that conversion factor. And you're in milligrams. And they want how many molecules of this compound. So sure enough, a conversion factor you're going to need is molar mass. Molecular mass. And that's always 1 goes with the mole. So for 1 mole of C17H22 ClNO, you have so many grams of C17H22 ClNO. So how many grams? Well, this is where you have to calculate the molecular weight or the molecular mass. They're used interchangeable using the periodic table. So we're going to do 17 times, I'm going to look up carbon. There's 17 carbons because of the subscript 17. And I see on the periodic table it has 12 point. You just need to go out like 2 digits past the decimal, okay? So 17 times 12 plus 0.1 plus how many hydrogens? 22. 22 times 1.008 plus how many chlorines? Yep, it doesn't have a subscript, so you know it's 1. So look at the periodic table, that's 35.45. How many nitrogens? 1. That number is 14.01. And then how many oxygens is 1? And that's 16.00. And you add that all up. And it's molecular mass, that's grams per mole. And you add that up and you should get 291.27 grams per mole. So for 1 mole of diphenylhydramine hydrochloride, there are 291.27 grams. That's its molar mass. So that gives us a second conversion factor right here. Second conversion factor. Now we can figure out our conversion factor plan. CF plan. So we start with our given, which is 25. Here it is, 25 milligram tablet. So you put that over 1. So, well, first of all, let's just, before we put numbers in, well, 25.0 milligram over 1. So that's a tablet. Now remember, what you have on the top units, you want on the bottom. So we're going to milligrams. Now, we're going to look at our conversion factor and we're going to figure out it wants how many molecules. So, where can we find molecules? Yep, there's molecules in our conversion factors, and molecules are connected to mole. And we're at milligram. So how, do you see anything? Yes. As you can see, the grams here is connected to mole. So we got to get to gram. If we get to gram, we can get to mole. Our conversion factor is going to be milligrams to gram to mole, and from mole to number of molecules. So then we can do that exact plan. So milligrams, now you know the SI units, the prefixes, hopefully by now you've memorized them. So you can go from milligrams to gram, and you should know that that's 1,000 little milligrams into 1 gram. That's going to cancel out our milligrams. And then if we have grams on top, we don't want grams, so we're going to put it on bottom. And we can go from grams to mole. And that is the molar mass of the molecule that we just figured out, the C17H22Clno. So that number will be, with the grams, 291.27 grams per 1 mole. And then we can go from moles to number of molecules by Avogadro's number. So 1 mole equals 6.022 times 10 to the 23rd molecules. So when you put this in your calculator, you're going to type in 25.0, divide by 1,000, that number divide by 291.27, and then times, and in my calculator I have to do 6.022 second function EE to the 23rd equals. Make sure your calculator can work because you're going to need it this week. When you work that problem out, your answer should be let's see, what should your answer be? Is that right here? Okay, hold on just a second. I'll work it out real quick. So when you type this in your calculator, and we're going to go with 3 significant figures because of the 25.0 given, your answer should be 5.17 times 10 to the 19th molecules of C17H22Clno. The next problem is grams, moles, and atom conversions. This is problem 3-5. Calculate the following in 4.71 grams of lithium phosphate. You all see that that's lithium because lithium is a cation in group 1 on the periodic table. It gets the name lithium, just like on the periodic table. And then the PO4 is a polyatomic, PO4 3-. You should know the charge, and you should memorize its name is phosphate. So you should be able to recognize that that's lithium phosphate. Okay, but the question's asking you for A to calculate the lithium plus ions. And when you look at this, you have lithium is +1, phosphate is 3-. There's 1 phosphate because there's no parentheses, right? And then there are 3 lithium ions. So there's going to be 3 lithium ions. This is going to be important, that number 3. Because the conversion factor you're going to need will be 3 moles of lithium cation equals 1 mole of lithium phosphate molecule. So that will be a conversion factor you need. So what's our given? Our given is typically always the number with a unit, so 4.71 gram by itself. So you're going to start with 4.71 grams of lithium phosphate. You're going to put that over 1, and you're going to put gram on bottom. And it wants the number of lithium ions. So when it wants the number of something, we're going to have to use Avogadro's number. So we're trying to stack up our conversion factors here to solve the problem. So here for 1 mole of lithium 3 phosphate, we have 6.022 times 10 to the 23rd. Well, actually, that's not 1 mole. This is actually going to be 1 mole of lithium ions. We have 6.022 times 10 to the 23rd ions. Okay. So it's really asking us, what's the number of ions? The number of ions. How many ions? Our plan then is going to go from, we're given grams, and we can go from grams. And this is important to put the actual formula because we're going to switch from lithium phosphate to lithium. And when you have to switch from an element to another element or a compound to another compound, you need to put that in your conversion. So we're going to go from lithium phosphate grams to moles of lithium phosphate. And then for moles of lithium phosphate, we're going to convert to a substance here. And you go from, we call that the mole to mole bridge. And so, and you look at the subscripts here. So basically for 1 mole of lithium phosphate, you're going to have 3 moles of lithium plus lithium ion. But it didn't ask for moles of lithium ion, it asked for how many. So then you're going to have to do Avogadro's number of how many. So the number of ions. So let's rewrite this down here. So you take 4.71 grams of lithium phosphate over 1, that's your given, and we're going to put grams right here, grams to mole. We're going to keep that formula in there, lithium phosphate for 1 mole of lithium phosphate. But we don't want mole of lithium phosphate. This is molar mass, by the way. So in molar mass, the 1 always goes with the mole, and then this you're going to have to find from the periodic table. We'll talk about that again. That's adding up the molecular mass of 3 lithiums plus 1 phosphorus and 4 oxygens. So we'll calculate that in a second. Okay, so for 1 mole of lithium phosphate, we go from grams to gram. Now we want mole to mole. So for 1 mole of lithium phosphate, you have 3 moles of lithium ion. And you know that from the subscript. But it doesn't ask for how many moles, it asks for how many. So for 1 mole of lithium ion, you have 6.022 times 10 to the 23rd lithium ions. So before we actually put that in our calculator, we're going to have to calculate the molar mass of lithium phosphate. So you have 3 lithiums, and you have 1 phosphorus, and you have 4 oxygens. So this ends up being, if you look at the periodic table, you see lithium is 6.94. You got 3 of those. Phosphorus is 30.97. You only have 1 of those. And then oxygen, you have 4. 4 times 1600. And you add that up, and you should get about 115.793 grams per mole. If you put that in your equation, 115.79 grams, you put in your calculator 4.71 divided by 115.79 times 3 times 6.022 times 10 to the 23rd. And my answer was see if I can erase that. Yeah, that's nice. Okay. 7.35 times 10 to the 22nd lithium ions. And note, whenever you're dealing with a big number like Avogadro's number, you're going to have to, you should have exponents. So does the number make sense? And it does. Okay, that's part A. Now the other part of this question is how many grams of oxygen is in this compound. So grams of oxygen. So let's rewrite this here. What do we have? We have 4.71 grams of lithium phosphate. That's our given. And the question is how many grams of oxygen? And in this case, go with just oxygen, not O2. So what's our plan? Our conversion factor plan? Well, we're starting at grams, but it's grams of lithium phosphate. And we're switching over from lithium phosphate to an element oxygen. So we're going to have to go, the only way you can go from change of elements or change of compounds is what we call the mole to mole bridge. And in this case, since the elements are within the formula here, you're going to find this in the subscripts for your numbers to solve the problem. So we're going to go from grams of lithium phosphate, we have to go to moles of lithium phosphate. And from 1 mole of lithium phosphate, so for every lithium phosphate, we're going to have mole of oxygen, and in the subscript here, it's 4. We'll have 4 moles of oxygen. Did it ask for moles of oxygen? No, it asked for grams of oxygen. So then we're going to have to go from mole of oxygen to gram of oxygen. And you'll find that using the molar mass, the periodic table, where 16 grams equals 1 mole of oxygen. So now that we have our conversion factor plan, let's put in our numbers and solve our problem. 4.71 grams of lithium phosphate over 1. We don't want grams, so we're going to put grams on the bottom of lithium phosphate for 1 mole of lithium phosphate. Let me get my 3 in there. We've already solved this molar mass. We added it up in part A, and you can see here it's 115, so 115.79 grams per mole. So the grams cancel out. Now for 1 mole of lithium phosphate, so write that down the bottom. For 1 mole of lithium phosphate, we have, we want to go to oxygen, we have a 4, so we have 4 moles of oxygen. We have 4 oxygens in every 1 mole of lithium phosphate, and then you write for 1 mole of oxygen, We look at the periodic table. This is called the molar mass. We have 16.0 grams of oxygen. And the grams of lithium phosphate cancel out. The moles of lithium phosphate cancel out. The moles of oxygen cancel out. And if we put in our calculator 4.71 divided by 115.79 times 4 times 16, you should get the answer. We're going to 3 significant figures because that's what's in our given. You should get the answer 2.60 grams of oxygen. Okay, this is problem number 3-6. What is the formula for copper to phosphate? Well, copper is a transition metal, and the Roman numeral +2 means it's a charge +2. Phosphate, you've memorized those polyatomics, anions, PO4 3-. The overall charge needs to be 0. So we're going to end up having 3 coppers and 2 phosphates. So our formula should be copper 3, parentheses, because we're going to need more than one polyatomic anion, PO4 2. And then you check that. So your cation, you have 3 times +2 is a +6. 3 times 2 is +6. And then 3 minus and 2 minus 6, and for your anion, is an overall sum 0. So the question is, how many atoms? How many? So you're going to need Avogadro's number. Remember, if you have how many, anything, shoes, molecules, particles, how many, you're going to do Avogadro's number. So that's going to be in your conversion factor. And your given is the number with the unit. So your given, where you're going to start, is 8.40 moles of, to keep your formula that you just wrote, Cu3 parentheses PO4 2. And that will be over 1. Now, what is your conversion factor plan? Well, your conversion factor plan, you are at mole of copper 3 PO4 2. And what is written on the top is written on the bottom. So for 1 mole of copper 3 PO4 2, what's it asking for? How many atoms of phosphorus? So notice you've changed. You've gone from Cu3 PO4 2 to phosphorus. So the only way that you can convert copper phosphate to phosphorus is what we call the mole-to-mole bridge. And if you look for 1 mole, for every mole of copper phosphate, you have 2 moles of phosphorus, because you get the 2 here times the understood 1. 2 times 1 is 2. So here you have, for 1 mole of copper phosphate, you have 2 moles of phosphorus. And what did it ask for? How many atoms? And Avogadro's number, so you know you can do 1 mole of phosphorus for 6.022 times 10 to the 23rd atoms of phosphorus. Be sure to keep your element and your formulas in your equations and your dimensional analysis, or otherwise you'll make a mistake. So you get your periodic, and so if you see mole of copper phosphate divided by mole of copper phosphate cancels out, mole of phosphorus cancels out to give you atoms of phosphorus. So you put that in your calculator, 8.40 times 2 times 6.022 times 10 to the 23rd, and your final answer will be 1.01 times 10 to the 25th atoms of phosphorus. Notice that we pick, since our given has 3 significant numbers, our answer has 3 significant figures. The next problem is 3.7. The question is, how many moles of nitrogen are in 0.209 grams of nitrogen? Now notice nitrogen and oxygen are both nonmetals. On the periodic table, they're both nonmetals. So how would you call this? That would be a molecular compound. So we're going to call that di. And this is where we use our prefixes. Dinitrogen. We don't use mono there. Oxide. Dinitrogen oxide. 3-8. A sample of probably propane. You don't have to know that it was propane, but C3H8. Then you want to go from mole of hydrogen to gram of hydrogen. And then you also do the same thing for, you already have atoms of carbon from this problem here, to mole of carbon to gram of carbon. And this is molar mass, so you can use the periodic table to get those conversion factor numbers. So doing this, it's 6.40 times 10 to the 24 atoms of hydrogen, which you got from the given in the problem. Avogadro's number is 6.022 times 10 to the 23rd atoms of hydrogen in 1 mole of hydrogen. And for 1 mole of hydrogen, you have 1.008 grams of hydrogen. When you put that in your calculator, 6.40 times 10 to the 24th divided by Avogadro's number times 1.008. Actually, let me do that real quick. 6.40 second EE to the 24th divided by 6.022 seconds EE 23rd equals times 1.008. That is 10.7127 grams of hydrogen. At the end, I will round. Now we have to do the same answer with carbon. We worked out 2.40 times 10 to the 24 carbon atoms over 1. We use Avogadro's number, 6.022 times 10 to the 23rd carbon atoms in 1 mole of carbon. And then 1 mole of carbon, periodic table is 12.011 grams of carbon. So carbon atoms cancel out, mole of carbon to give us gram of carbon. We put that in our periodic table, our calculator. 2.40 e to the 24th divided by Avogadro's number, e 23rd, times 12.011. That will be added to the grams of hydrogen, which is 40, so the answer is 47.868 grams of carbon. When I add that to the 10.7127, I get a final answer 58. We want 3 significant figures. 58.6 grams is the total mass of the sample. The next problem, which we call 3-9, is 8 grams, moles, and atoms conversion. A 59.4 gram sample of compound X4O6 contains 14.4 grams of oxygen atoms. What is the molar mass of element X? So the way I work this is I take the mass of the compound, 59, because it's a binary compound, 59.4 grams sample, minus 14.4 grams of oxygen equals 44.6 grams of X. Now, we base this on 100 grams sample, 14.4 grams, the ratio, divided by 59.4 grams of the sample. So that is 24.24% oxygen. And then the other compound here, the other one is X, that's oxygen. 44.6 grams divided by 59.4 grams of the sample times 100%. Guess you need that times 100% as well. Gives you 74.07%. Sorry about that. That would be X. Now, this should look now like a problem you've seen before, where you convert the grams the percentages into grams. And then you use the periodic table. So now you can do this percentages. You just kind of convert that into grams, and then you use the periodic table for the molar mass, because your goal is to get the subscripts. So in order to do that, you're going, basically it's going to look like this. So let's do oxygen. 24.24 grams of oxygen over 1. And if you look at the periodic table, for 16 grams of oxygen and 1 mole of oxygen, that gives you 1.5 mole of oxygen. Now the next problem, the problem is here we don't know what X is. So you're going to take 74.07 gram of X over 1, and we don't know what the gram of X is for 1 mole of X. But we know that it is actually 1.0 mole. And how do we know that? Because the formula is actually given to us. The formula here is X4O6. So you take each one of these, you got 1.5 mole of oxygen, so you divide both of these by 1.5. Once you divide the 6 by 1.5, which you got here, so 6 divided by 1.5 is a factor of 4. So a factor of 4. So then you're basically, you can tell that, so if you take 1.5 times 4 is 6. What number times 4? Because this is definitely 1.5. What number times 4 gives you 4? That would be 1. So your semi-empirical formula is X1 O 1.5. So if you multiply both of these subscripts by 4, it'd be X to the 4th and oxygen subscript 6. So now, that's why you know it's 1.0 mole. So you can take 74.07 grams, kind of the proportion, divided by X equals 1.0 mole of X. And so if you divide both sides by 1, you find that your answer is 74.07 grams. You look at the periodic table. If you look at the periodic table, which element has close to 74.07 gram per mole? It should be arsenic, so that would be As4O6 is your molecular formula. This problem is 3-10. This is empirical formulas. An empirical formula is when you're given percentages, the first thing you want to do is you want to convert them to gram. So you want to convert them all to gram. Percentages is like 100, so it's based on 100 grams. So we'll go with 54.53 grams of carbon, 9.15 grams of hydrogen, 36.32 grams of oxygen.
And you're going to put this all over each one of these under 1, because this is your given. And then you don't want grams, so it's going to be grams of carbon into 1 mole of carbon. So the second thing you're going to do is use your molar mass, which you're going to get from the periodic table, to convert them to moles. And here for grams of hydrogen for 1 mole of hydrogen. This is grams of oxygen for 1 mole of oxygen. So if you look at the periodic table, you'll see that the molar mass for carbon is 12.011.
Excuse me.
The molar mass for hydrogen is 1.008. And the molar mass for oxygen is 6.00. So you put this in your calculator, 54.53 divided by 12. You should get 4.54 mole of carbon. You do this for each one. 9.15 divided by 1.008 should give you 9.08 mole of hydrogen. 36.32 grams of oxygen divided by 16 grams of oxygen gives you 2.27 mole of oxygen. What you have here then, if you can imagine, is carbon with little subscripts 4.54. I would always take this out to about 2 digits past your decimal. You have H 9.08, and then oxygen is subscript 2.27. Now you don't normally see fractions like that in the subscripts, so it's not right. Okay, you're going to have to reduce the lowest terms. So when you reduce the lowest terms, this is the third thing you do. You divide by the smallest subscript. And in this case, it's 2.27. And you do this to each one of these numbers. And then you're going to get whatever is closest to. So when you do that, 2.27 divided by 2.27 is going to be a 1. 9.08 divided by 2.27 is close to 4. And 4.54 divided by 2.27 is 2. So this works out to be C2H4O1. We don't put 1 in there. And this will be your empirical formula. The second part of this question, they actually give you the molar mass. So whenever you're given the molar mass, if you're given the molar mass of the compound, then you can actually solve for its real formula, molecular formula. So in order to solve for the molar formula, you're going to have to, first thing, is calculate the molar mass of the empirical formula. So we just worked out the empirical formula, C2H4O. So when you do this on the periodic table, you've got 2 carbons times 12.01 gram per mole plus 4 hydrogens times 1.08 gram per mole plus 1 oxygen 16.0 gram per mole. Your empirical formula ends up being 44.05 gram per mole. Now you were given in your problem you have 132 atomic mass unit. This is interchangeable for grams per mole, so I just go ahead and write that grams per mole when I see it. And now you divide, so you're taking the molecular formula, the molecular mass, and you're going to divide it by the empirical mass. So you're going to divide this by 44.05 gram per mole. And it's going to be unitless. When you do that, 132 divided by 44.05, you're going to get something that's 2.996. That's pretty much 3. Now you can multiply your empirical formula. So this is your empirical formula here that you worked out in the first part. You can multiply each subscript by 3. So C, what's 3 times 2? 6. 3 times 4 is 12, and oxygen would be 3. So your empirical formula should be C6H12 oxygen, which is O3. Problem number 311. Calculate the percent composition by mass of each element in, what is that? Potassium perchlorate. Page 109 tells you how to do the mass percent of an element. It's a formula you need to memorize of X equals mass of element X and 1 mole of your compound divided by the mass of 1 mole of the compound. So this is the part over whole times 100%. So if we want the mass of the compound for the bottom, the bigger number, we're going to have to do the formula weight, or the formula mass, of potassium perchlorate. So we have 1 potassium, which is 39.0983, plus 1 chlorine, 35.4527, plus 3 oxygens, which is 3 times 00, which is 48 for oxygen. You add these up, you should get a molar mass, a molecular mass of 122.55 gram per mole. So that's going to be your bottom number, right there. You want the mass of each element. So we're going to have to do this 3 times, because we got 3 elements, right? We got potassium, chlorine, oxygen. So now we look at the periodic table, and you only have 1 potassium, so it's 39.0983 gram per mole. So this is for potassium divided by the mass of potassium perchlorate divided by 122.55 gram per mole times 100%. That equals 31.90% potassium. Now we got to do the same thing for chlorine. So the mass of the chlorine is 35.4527 gram per mole divided by the mass of the entire compound, 122.55 gram per mole times 100% gives you 28.93% for chlorine. The last one is oxygen. Now we have 3 oxygens, so you're going to take 3 times 16.00 gram per mole over the whole mass of the compound, which is 122.55 gram per mole. That works out to be 48 gram per mole divided by 122.55 times 100% should give you 39.17% oxygen. These should all total up to 100% to check that. And that is how you do mass percent of each element in a compound. The last problem of this recitation problem set is 3-12. And this is a balanced chemical equation. So we have propane, C3H8 plus oxygen, yields carbon dioxide plus hydrogen. Now what I do is I make myself a table. So I do a reactant table, and I do a product table. And I kind of take inventory because of the conservation of mass. That's right. So whatever the mass we have on the reactant side, we have to conserve that mass on the product side. And that is why we balance chemical equations. So what elements do we have? We have carbon, we have hydrogen, and we have oxygen. And we have the same thing on the reactant, on the product side, carbon, hydrogen, and oxygen. So now the first thing I do is I take inventory. So I'm going to figure out how many moles we have of each. Well, we have 3 carbons, and over here we have 1 carbon on the product side. On the reactant side we have 8 hydrogen. On the product side we have 2 hydrogen. On the reactant side we have 2 oxygen, and we have 3 oxygen on the reactant side. So I usually just take one element at a time. Now I want to point out something. Never, ever, ever, never change your subscript. If you change your subscript, these are the little numbers, then you change your compound. You can only change coefficients. And coefficients are the big numbers that you put in front of the elements or molecules or the compounds. So just always remember that. Note that.